So let us start with what is quantum computing. So quantum computing is an emergent field of computer science that makes use of unique features of quantum mechanics like superposition and entanglement to solve problems beyond the ability of most powerful classical computers. And the thing is that quantum computer is not just a modified version of classical computer. So we cannot make an LED by modifying an incandescent lamp. Just like that, we cannot make a quantum computer by modifying or a classical computer by increasing the number of chips or something like number of registers or something like that. So that is the basic difference. It is entirely different. The working is entirely different. So in my talk, I will mostly concentrate on two key aspects of quantum mechanics that are mostly used in quantum computing, that is superposition and entanglement. So before that, let us consider a statement made by Feynman in 1982. So Feynman observed that there are essential difficulties in simulating quantum mechanical systems on classical computers. Computers based on quantum mechanics would allow us to avoid those difficulties. So it was actually Feynman who pointed out the need for a quantum computing system. But so we can explain it further. So before that, there was the Moore's law. Gordon Moore was the founder of Intel Corporation, and he made a prediction. I think it is in 1960s. It was in 1960s. He predicted that the computing speed or the computers will grow, the computing speed will grow, or the computing facility will double in every 18 months. Actually, at that time it was 2 years, later it was modified as 18 months. So, but in order to increase the capability of computing, we have to increase the number of transistors that can be accommodated, that can be fabricated on a chip. So that means the size of the transistor should be reduced. But quantum mechanics imposes some conditions, some limitations on that. So Moore's law is constrained by some quantum mechanical limits. So that is a drawback of classical computing systems. Then another drawback with classical computing is that so certain problems like factoring of large integers, prime factoring of large integers, so they are not efficient using classical algorithms. And another area is where the simulation of molecules, very complex molecules, so simulation of complex molecules, in those situations also classical algorithms fail. So a quantum computer is a necessary, a quantum computer is a necessity in those aspects. So quantum computing offers significant speed up for specific problems like Shor's algorithm. Shor's algorithm is actually related to the factorizing algorithm. It was the first quantum algorithm. So even though Feynman pointed out the need for quantum computing or the limitation of classical computing in 1982, only in 1994, Shor demonstrated that using some quantum algorithms, we can make the factorizing problem easier. So he first demonstrated how to crack or how to factorize large integers using a quantum algorithm. It was Shor's algorithm. So actually it was the beginning of quantum computing. So the area of quantum computation or quantum computing began, we may say it began in 1994. So later came Grover's algorithm. It was a searching algorithm. And so the quantum computing and quantum information theory has implications in cryptography, material science, and AI. In cryptography, because in classical cryptography, one of the techniques used is the inefficiency of classical algorithms to factorize. That is used in classical cryptography. And what Shor demonstrated was that it can be factorized using a quantum algorithm. So it has some significance in cryptography. Then surely material science and chemistry simulations are made easy using, because in chemistry and in material science the number of molecules or number of particles is very large. So in such cases a quantum computer can better perform that, can perform better.
The main advantage of quantum computing is the speed, isn't it? Speed, because in cryptography you have to determine whether something is factorizable or not.
Yes.
The answer to this question has to come as soon as possible, as fast as possible. So quantum computing is useful in that way. Is it the sense in which you are saying that quantum computing is superior to classical computing? Or another way, that is, more data can be stored in a quantum computer. Therefore, more verifications can be done than in a classical computer. I don't understand that point.
In cryptography, a system can be cracked if it is based on classical computing. But if quantum computing is used, it is not easy to hack a system. So in computer science, the complexity is measured in terms of the resources required, or the memory space and time required. And in computer science, or in complexity is measured whether it is the algorithm requires a polynomial type function or an exponential type. If the input size is very small, the polynomial functions will grow faster than exponential functions. That we can see by an example. If n is equal to 4, suppose we have a polynomial type function, n raised to 5. It is only 1024, but if you consider an exponential function like 5 raised to n, it is 625. So n raised to 5 is greater than 5 raised to n for a small input size, if n is very small. But if you consider a
function of what? Function of time, computing time, that is
input size. Input size.
Input size.
എന്നുള്ള ഇൻപുട്ട് സൈസ്
So,
എന്നുള്ളത്
because a quantum computer, the input size can be
very large, 2 raised to
very large.
exponential ആവും.
That brings me back to my point at the beginning. The usage of more data, superposition principle will give more data.
2 raised to n states are available. So my aim is to only show that, so for when the input size is large, exponential growth is there, and classical computers are unable to, or they are inefficient to handle exponential growth. But sometimes exponential growth is there. So in simulations and factorization problems and in optimization problems is also, the input size will be very large. So exponential growth is there, and classical computers are inefficient to handle such situations. So there comes the relevance of quantum computers. So these are the potential applications of quantum computing. So one is in simulations, then optimization problems, then in cryptography, then also in AI, quantum computing has some applications. Now, before going into the details of quantum computing, it is good to go through some basic aspects of quantum mechanics. So, I think most of the students are familiar with the basics of quantum mechanics, but take this as a review. So the thing is that in quantum mechanics, the states are taken as vectors in some space, in a complex vector space. So associated with any isolated physical system is a complex vector space with inner product known as the state space of the system. The system is completely described by the state vector, which is a unit vector. That means it is normalized. Usually it is assumed to be normalized. And in Dirac notation, the state vector is called a ket, and it has this particular notation. And it's the dual space of the ket space is called the bra space, and both ket vector and bra vector contains the same information. So a ket vector is assumed to contain all the known information about the system. And so we are more interested in two-dimensional case, two-dimensional complex vector space. So C2. So in a two-dimensional complex vector space, every state ket can be expressed as a linear combination of two basic kets, ket 0 and ket 1. So ket psi, the state ket, general state ket can be expanded as a linear combination of ket 0 and ket 1. And in general, ket alpha and ket beta, alpha and beta are complex numbers. Now, so these are abstract vector space. So in order to visualize it better, we use matrix representation, and kets are usually represented by column vectors, column matrices, and in particular ket 0 is usually denoted as the column vector 1 0, and ket 1 is denoted as 0 1. And actually these are eigenvalues of the matrix 1 0 0 minus 1 with eigenvalues plus 1 and minus 1. Okay. So when it acts on, when this square matrix acts on 1 0, it will give 1 0, and when it acts on 0 1, 0 the matrix get multiplied by minus 1. So and in this notation, in matrix representation, bra vectors are represented by row matrices. Then the idea of inner product can be implemented better using the matrix representation. So we can see that the inner product of ket 0 with bra 0 is 1, and ket 1 with bra 1 is 1, and the other two inner products are 0. So that shows the orthonormality property. Now, in addition to ket 0 and ket 1, there are possible base kets in C2. They are plus ket, 1 by root 2 into ket 0 plus ket 1, and minus ket is 1 by root 2 into ket 0 minus ket 1. Then another possibility is, another base ket is, another set of base kets are ket I, 1 by root 2 into ket 0 plus I times ket 1, and ket minus I is 1 by root 2 into ket 0 minus I times ket 1. So those who are familiar with Sankara may find it confusing. The notations are somewhat different. So what Sankara used for ket, so here what Sankara denote by ket plus and ket minus are here denoted by ket 0 and ket 1. അവിടെ SX പ്ലസ് കെറ്റ് SX പ്ലസ് എന്ന് ഡിനോട്ട് ചെയ്യുന്നതാണ് ഇവിടെ കെറ്റ് പ്ലസും, അതുപോലെ കെറ്റ് SX മൈനസ് എന്ന് സാക്രയിൽ ഡിനോട്ട് ചെയ്യുന്നത് കെറ്റ് മൈനസ്, അതുപോലെ അവിടെ കെറ്റ് SY പ്ലസ് എന്ന് സാക്ര ഡിനോട്ട് ചെയ്യുന്നത് ഇവിടെ കെറ്റ് ഐ. ക്വാണ്ടം കമ്പ്യൂട്ടിങ്ങിൽ യൂസ് ചെയ്യുന്ന നൊട്ടേഷൻ ഇതാണ്. അതുകൊണ്ടാണ് ഞാൻ ഈ നൊട്ടേഷൻ ഫോളോ ചെയ്തത്. പക്ഷേ സ്റ്റുഡൻസിനൊക്കെ അത് ഒരുപക്ഷെ കൺഫ്യൂസിങ് ആയിരിക്കും. അവർ മറ്റേ നൊട്ടേഷനാണ്. അവിടെ അതുമായിട്ടൊരു ചെറിയ ഡിഫറൻസ് ഉണ്ട് ഇവിടെ. So an eigenvector, all of you know from linear algebra, this is the definition of an eigenvector, and so we consider a poly Z operator, It is ket 0 into bra 0 minus ket 1 into bra 1. So its eigengets are ket 0 and ket 1 with eigenvalues plus 1 and minus 1 respectively. Then this is definition of a Hermitian operator. Then eigenvalues of a Hermitian operator are real. So hence in quantum mechanics, observables are represented by Hermitian operators. Now, most importantly, there is the measurement postulate. So that is very much important in quantum mechanics. So when we in quantum mechanics, when we measure an observable, say A, before that measurement, it is in an arbitrary state. So it is in a superposition state of its eigengates. So if we assume that before measuring an observable A, the system is in a superposition of eigenstates of eigenstates of the operator A. So ket psi is summation over I Ca into ket Vi, where Ca's are some expansion coefficients. Then, and when we measure the observable A, the system will collapse into one of the eigenstates. But the thing is that we cannot a priori say to which eigenstate the system will jump into. We can say only the probability for jumping into a particular state, and that probability is proportional to square of that expansion coefficient, or it is proportional to Ca square. For example, in our case, if we measure the Z component of spin for a spin half particle, before measurement we can assume that the system is in a superposition of SZ operator because we are measuring the Z component of spin. So before that it is in a superposition of ket alpha into ket 0 plus beta into ket 1, and after measurement it will jump either into ket 0 or into ket 1. Now, so let us make a quick comparison between classical computing and quantum computing. In classical computing, as all of you know, the basic units are 0 and 1, but in quantum computing they are qubits, ket 0 and ket 1, and possible states are only, in classical computing only possible states are 0 and 1, but in quantum computing any superposition of ket 0 and ket 1 are possible. So in classical computing the state it is deterministic, but here it is probabilistic. And if you consider a typical gate, single input gate, there is only one single input gate in classical computing, that is the NOT gate. But here, analogous to that, we have poly X gate. So it is nothing but actually the poly sigma matrix, sigma X. So in classical computing we have Boolean algebra, here we have linear algebra. So the basic difference is that, so if you consider for example an AND operator, by observing the output we cannot say what were the inputs. It is irreversible. Classical gates are irreversible, but here these are unitary matrices. In quantum computing all gates are unitary matrices actually. So we can invert them because they are unitary matrices. So we can get the all gates are reversible in quantum computing. Then another thing is that the state space is linear. It is proportional to the input size in classical computing, but in quantum computing it is proportional to 2 raised to n. So many states are available. That is that.
Computation itself is a unitary matrix, isn't it?
In quantum computing.
Quantum computing. Superposition is produced by means of a unitary operator.
Okay.
Therefore, it is reversible.
Reversible.
It is simple mathematical property.
Yes. So state space is 2 raised to n in this case. Now, so usually the qubits are, so for the representation of qubits we use what is called the Bloch sphere. The ket 0 and ket 1 are the pole, north pole and south pole of this Bloch sphere. So any arbitrary qubit can be represented like this using theta and phi. So these are the single qubit gates, poly gates, Hadamard gate. So these are the matrices corresponding to those. So these are the operations. The poly X operator, X gate acting on ket. It is a bit flip operator. Bit flip operation. X acting on ket 0 will become make it ket 1 and vice versa. And Z acting on ket 0 produces ket 0 itself. But Z acting on ket 1 is will multiply it by -1. Then Hadamard gate makes when Hadamard gate acts on ket 0, it makes a superposition state. Similarly, when it acts on ket 1 also, it makes another superposition state. But again, if Hadamard gate acts on this, it will give either ket 0 or ket 1. So the square of Hadamard operator is identity operator. So these are the physical realizations of qubit states. So the two polarization states, vertical and horizontal polarization states of polarization states of light, then of a photon. Then another thing is spin half system, spin up and spin down states. Then comes two-level artificial atoms. There we can identify the ground state with ket 0 and excited state with ket 1. So there are multiple qubit states can also be produced by taking the tensor product of single qubits. Then there are two types of multiple qubit states. So states which can be written as the product of two qubits is called a product state, but there are some states which cannot be written as, or it cannot be decomposed into single qubit states. They are called entangled states. So in this case, these examples are maximally entangled states. So they are called Bell states. So entanglement means, so if we measure the property of one qubit, we can automatically automatically know the property of the other, how far they apart, even if they are far away, at faraway points. So hardware advancement, as far as hardware and advancement is concerned, I think IBM has succeeded in producing 400 qubit states up to that. Then qubit technologies, different technologies are made use in realizing qubits. Then challenges, the main challenge in quantum computation is the decoherence. Another quantum property, decoherence. Then, so in AI also, so the combining AI with quantum computing is also developing.
The output of computation is obtained by decoherence, isn't it?
Yes, sir.
That is the importance.
Sure.
The computer, input, finally it should give the output. That is possible only through
decoherence. Decoherence, lack of അതായത് മെഷർമെൻറ്റ് നടത്തുമ്പോൾ സൂപ്പർപോസിഷൻ ആണെങ്കിലും ഫൈനലി ഔട്ട്പുട്ട് വേണമെങ്കിൽ മെഷർമെൻറ്റ് നടത്തുമല്ലോ. മെഷർമെൻറ്റ് നടത്തുമ്പോൾ ഈ കൊളാപ്സ്, ഇത് മെഷർമെൻറ്റ് തിയറി അനുസരിച്ച് ഏതെങ്കിലും ഒരു സ്റ്റേറ്റിലേക്ക് കൊളാപ്സ് ചെയ്യുന്നു. ഇപ്പോൾ റിട്രീവ് ചെയ്യുമ്പോൾ നമുക്ക് ഫൈനൽ ഇൻപുട്ടിൽ ഈ ആംബിഗ്വിറ്റി വരുന്നില്ല. ഇവൻ ദോ ഇറ്റ് ഈസ് എ സൂപ്പർപോസിഷൻ, ഇത്രയും സ്റ്റേറ്റ്സ് അവൈലബിൾ ആണെങ്കിലും ആൻസർ നമുക്ക് കറക്റ്റായിട്ട് കിട്ടണം.